Let's round out our videos on word problems with a video talking about conditioning. Sometimes you encounter a situation in which the objects that are in your question depend on mutually exclusive properties. Let me give you two examples. If you think about students who are in high school, they're either in 9th grade, or 10th grade, or 11th grade, or 12th grade. You're not in both 10th grade and 11th grade. Every student in high school is in one and only one of those grades. Here's another example. Binary words that have 4 digits, that is, like 0000 or 1101, we can condition on how many ones they have. You can either have 0 ones, or you could have 1 1 in the word, or 2 ones in the word, or 3 ones in the word, or 4 ones in the word. But you can't have 2 ones in the word and at the same time have 0 ones in the word. Every binary word is in one and only one of these cases. In this situation, you can say that your larger set is partitioned into these smaller sets. So we have a set A, and it's partitioned into sets A sub I. Like this, A is equal to A1 union A2 union A3 up until A sub K. That is, every element is in at least one of those sets. But further, these sets are disjoint. The intersection of any two of the sets is the empty set. So this is a partition of the set capital A into smaller sets. The key thing that a set partition has is that every element of A is in one and only one of the A sub i's. It's in exactly one of the A sub i's. The language that we use here is the idea of conditioning on this property. So if we let capital H be the set of high school students, then we can condition on what grade the student is in. There's some students who are in 9th grade, there's some students in 10th grade, there's some students in 11th grade, there's some students in 12th grades, and there's no overlap between these sets. So we can define H9 to be the first set, H10 to be the second set, H11 to be the third set, and H12 to be the fourth set, and we have that capital H is equal to H9 union H10 union H11 union H12. Similarly, if we look at the set of binary words of length 4, we can condition on how many ones there are in the word. The set of words with 0 ones in it is just 0000. The set of words with 1 1 in it is 1000, 0100, 0010, and 0001. So we'll put those in B1. Similarly, we can define B2, B3, and B4. The set of all binary words is broken down into 5 sets that have no overlap. When you have a set that has a natural partition into disjoint subsets, negating a condition is a straightforward thing to do. So if we ask the question, which high schoolers are not seniors? Well, we've written down H is equal to H9 union H10 union H11 union H12, and there's no overlap between them. Seniors are this set H12, and if we take that set out, the only things that are left are H9 union H10 union H11. Similarly, we might ask the question, how many binary words of length 10, okay, so much longer ones, have at least 2 ones? Well, we have words that have 0 ones, 1 1, 2 ones, 3 ones, 4 ones, etc. And if we're asking how many binary words have at least 2 ones, that's this set. It's actually easier to think about what's the opposite of at least 2 ones. The negation of at least 2 is less than 2. These numbers are all integers, so the only things that are left are the sets B0 and B1. So instead of adding up all of these values of B2 up to B10, we could instead figure out how much is there in the whole set and remove just the elements that are in B0 and B1. So the key concept here that we're discussing is that if you need to negate something like greater than or equal to 2, the negation of that is less than 2. And we can use that to our advantage in word problems. Okay, that's it. We'll see you next time. Take care.